happens. Even in the regular classes that happens. So I was here at 10 minutes before 10 and didn't find anybody. And I was worried that maybe, they've all given up on me. But thankfully there's at least a dozen of you that still have some faith in me. So thank you very much for that. Okay, so I think yesterday's lesson was a brief introduction on the area of reliability. We spoke about the definition of reliability. We spoke about the background where reliability was applied initially in military applications and aerospace applications, and then later on to power systems, nuclear engineering in particular. But it should be appreciated that these reliability evaluation techniques can be applied to many systems, not just to electric power systems. I know most of us have the background in power engineering, therefore we tend to use these techniques for that, which is perfect because they were designed to be used for many, many systems, power systems being one of them. Then we spoke about the definition of reliability and the 4 components: the probability, the period of time that the product is supposed to function, the operating conditions encountered, and the adequacy. That means how do you define adequate performance of the component, which is a managerial decision, right? So then we moved on and we talked about the mean and standard deviation, right? So very basic, elementary mathematical expectation, more commonly known as the mean or the average. Now we are in a position to so now we are in a position to move on and actually start looking at reliability evaluation of engineering processes or systems. We are still in what we call as mission-oriented systems, so to speak. When we go on to continuously operated systems such as a power system or a control system, then we will talk about time-dependent reliabilities. So right now it is still time-independent values. So you will just use some number, 0.9, 0.8, 0.85, just to illustrate the concept, okay? So as you can see from here, many systems consist of various components which can be considered either to be operating in series or parallel or some sort of series parallel. And we start with some of the fundamentals. So starting at the series connection, which is also known as non-redundant system. Because non-redundant means there is no redundancy, right? Which means that everything must operate for system success. If one component fails, the entire system will fail. So series system is not in many ways desirable, right? You should not be connecting components or processes in series because it's kind of dangerous. As long as you know what you can expect, then it's okay. Maybe the process still requires you to connect them in series. So the reliabilities of those series components must be really, really high. Otherwise, there is a danger that your system will fail too often, right? Let's assume that we have two components A and B connected in series. No, this is not working. Yeah. And let RA and RB be the reliabilities of those two components or subsystems, or call them what you will. Yeah, RA and RB. This is an ominous start. Some loose connection. Right, so RA and RB are the reliabilities of those two subsystems, which of course is the probability of successful operation, right? That's how we define reliability. The probability that the system will operate for the period of time intended under the operating conditions encountered adequately, right? So that's why it is the probability of success. And the unreliability is the probability of failure in general. That's how we'll use the definitions. So the reliability of success will be equal to RA times RB, because the systems are in series. The product of the reliabilities will be equal to the system reliability. So in general, for n series components, RS is equal to the product of RI, where I goes from 1 to n. Yeah? And the probability of system failure or the system unreliability is 1 minus the reliability, so it is 1 minus RA RB. So we can write a general equation like this: the unreliability of the system Q. So we are going to use that notation throughout. R is reliability, Q is unreliability for now. Later on, when we go to continuously operated systems, we are going to change the notation slightly, and we are going to call availability and unavailability instead of reliability and unreliability, because power systems, you want to know whether they are available at some point in time in the future. So the reliability aspect deals with the availability of the equipment, the generator, the line, or the feeder, and so on. Okay. So back to this. This is the general form of the unreliability if you want to find for 2 or more components in series. Let's look at parallel system, which is a fully redundant system. Fully redundant. What does it mean? It means that only one component is required out of the 2. Yeah. So there is redundancy. There is extra reliability that you are going to incorporate in the system, right? Of course, you can put 3, you can put 4, you can put 5. I will show you through an example how that impacts the cost, yeah, and whether you need 5 components in parallel as opposed to just 2 or 3. Yeah, we'll see how much the reliability changes and what is the cost that you need to incur. But for now, yep. Okay, so that's the equation for 2 components. If we want to expand it to n components, then we can say that the unreliability of a parallel network comprising n components is a multiplication of Q1, Q2, Q3, Q4, Q5, correct? This stands for multiplication, correct? You all know that. And therefore, the reliability will be 1 minus Qi summed over I to n, okay? The product of all the unreliabilities. So we can easily appreciate that the system reliability for series systems will decrease if you have more series systems, and will increase when we have more parallel components. But of course, when you add parallel components, you are adding volume, you are adding weight, and you are increasing the system maintenance, not to mention the cost, right? So we'll see through an example a little later how the cost can be determined. So simple examples here: a 2-component series system contains identical components, each having a reliability of 0.9. Calculate the system reliability. It's very straightforward: 0.9 times 0.9, and therefore the unreliability is 1 minus reliability, which is 19%. Yeah. Another example: a system design requires 100 identical components in series. If the overall reliability must not be less than 0.99, what is the minimum reliability expected of each component? 100 of them connected in series, we want the overall reliability to be 0.99 minimum. So what should be the reliability of each of those 100 identical components? Yeah, they're not non-identical, they're all identical. So RS, as you know by now, RA times RB times RC times RD, right, for series system. So I going from 1 to 100 and the reliability of each component. So we know that RS must be greater than or equal to 0.99, and all the components are identical. So their reliabilities are R. We can just say that each one has a reliability of R. Then 0.99 must be equal to R to the power 100, right? R times R times R times R, all the way up to 100 components. So from here we can calculate that the reliability of each component must be 998, 9995. See, this is one of the problems when we study reliability, and when you go to your bosses and say that the reliability is 0.9998, 99995, he says, what the hell is this, right? So that's one of the problems. We are trying to quantify and trying to tell the management, hey, it is extremely reliable. But what they are really interested in is not this number. It's how much is it going to cost them to make that system that reliable. Yeah. And what will be the cost if you make it slightly less reliable or slightly more reliable? That's where the sensitivity studies also come into play. Yeah. So therefore, if we know the background, then we can look at sensitivity studies and try to expand the analysis. Another example, a system consists of 5 components in parallel having so and so reliabilities. Calculate the system reliability. Yeah. So you know that for parallel components, QP is equal to Q1 times Q2 times Q3 times Q4 times Q5. So we will calculate the unreliability first. So the total unreliability of the system is so small, e to the power minus 8. Therefore, the reliability is 1 minus QP. See, it's almost 1. I mean, how do you explain that? It's a series of 9s, yeah, all the way up to even the 9th or the 10th digit. So approximately 1, right?
Suppose after decimal, you have a 8 digit of 9, and I wanted to pick out the physical significance for my plan. That means the part here, how many seconds still we are on the list. Suppose 5 seconds is the list, and my desire is the 3 seconds according to my critical process and critical sign. So another, I have to keep on increasing to bring that scale, less than the 3 seconds.
Yeah. So I think this one has no connection with time, but it tells you how many components should suffice for your reliability to be at a certain level. You may not want 5 of them to be connected in parallel, right? Because the reliability is almost 1 now.
Out of 1, 100%, this much developed at least, but that can be derived in a second. And then only the utility of that from a planning point of view.
Yeah, so we'll come to the planning part, sir. This is just, again, very time independent probabilities. When we come to the time dependent probabilities, you can see the planning horizon a little bit better. Yeah, these are still very short term reliability calculations. You could call them mission oriented calculations. Okay. So we find that this is almost 1. Another example, consider a communication system consisting of a transmitter, a receiver, and an encoder. Some kind of a practical example. Failure of one causes system failure. So I didn't tell you that they are in series, but that sentence tells you that they are in series. So determine the reliability of maintaining communications without failure given the reliability of the 3 components. So quite straightforward, 0.79, yeah. Series components, the reliability will not be that high. Now, we have talked about series, we have talked about parallel. Obviously, not all systems are connected in those very simple configurations. So some of them now we see series parallel, parallel series, and then we try and compare. So if they are connected like this in series parallel, so 3 components in series, another 3 components in series, and this branch is in parallel with this branch. So how do we deal with these systems? Again, very simple analysis. These 3 are in series, so the reliability will be R1 times R2 times R3. These 3 are in series, so R4 times R5 times R6, and this branch is in parallel with this, so RA plus RB minus RA RB, right? So I think once you know the concept, then this follows very easily. So that's the reliability equation in the end, right? Another example, derive a general expression for the system reliability of the figure shown below. If all components have a reliability of 0.8, find the system unreliability. I'm asking you to derive the general expression first rather than just do the calculations, okay? Because you can easily do the calculations once you are given the number, but we want you to derive the expression first. So we have 2 components here in parallel. We can combine them to create another component, which I'm calling 6, and then 1, 2, and 6 are in series, and this branch is in parallel with 5. Yeah, so 1, 2, and 6 I'm calling 7, and then the eventual component I'm calling 8. So you know the process, right? Yeah, you start from here. These 2 components are in parallel. So you can say that the reliability is R3 plus R4 minus R3, R4, right? And then multiplied by R1 multiplied by R2. That's the reliability of this path. So then there are two paths, you know how to calculate, right? So that's how you will get the expression. So I've derived the expression over here. The idea is to get all the quantities in terms of R, everything in terms of R, yeah? So that's why you see the simplification here, the R6, because 6 is not our component, right? Our components are 1, 2, 3, 4, 5. 6 is an equivalent component. 7 is an equivalent component. So ultimately, I want to put all the reliabilities of components 1 through 5 in the expression. Okay, so that's the objective, which is why I'm doing all these simplifications. I'm getting rid of the R6 and Q6, yeah? And similarly, R7 and Q7, if they are there, I'm getting rid of them. So ultimately, you see it is R1, R2, R3, R4, R5 only, because those are my original components, right? And then, of course, after this, all the components are identical, we said, and their reliability is 0.8. So if we stick that number in this equation, we find that the reliability is 0.92288. And if you are asked the system unreliability, that will be 0.077. Again, not very difficult. These can be done by hand calculations quite easily. Now, I promised to show you what happens when we connect components in parallel and what is the implication of that. So this example shows us exactly that. A system component has a reliability of 0.8. Evaluate the effects on the overall system reliability of increasing the number of these components connected in parallel. So we know when components are connected in parallel, the Q of the parallel system is multiplication of Q1, Q2, Q3, Q4, Q5, right? We already said that. And RP is 1 minus QP, correct? So now we see number of components 1, the reliability is 0.8. When I add the second component in parallel, what will be the reliability? Remember, R1 plus R2 minus R1 times R2. So we'll find that that number is 0.96. So how much has the reliability improved by? 0.16. As a percentage, it is 20%, right? 0.96 minus 0.8 divided by 0.8, that's 20%. I add the third component, I will find using the equation, using this equation and this equation, I will find that the reliability becomes this. So how much is the incremental value? Yeah, it's 0.032 with respect to this, correct? And the total comparative improvement with respect to the origin is only 24% with respect to the original. You keep adding the components, you find that the comparative improvement is marginal, yeah? And of course, the incremental reliability is also going to be lower and lower and lower. So I think if you look at these two curves, it tells you a better story. The first curve is this one, comparative reliability over a single component. So this green curve is the comparative reliability. So you see that it is plateauing here. It is plateauing. After the third component, it doesn't change much at all. In fact, the greatest change occurs from the first component to the second component, right? The greatest change, the 20%, if we go back to that table, the greatest change takes place here. Here it's only 4% more. Here it's less than 1%. Here it's less than even 0.2%, and so on and so forth. So the second curve is the one in light green, and that is incremental reliability. Yeah, incremental reliability, you see again, the addition of the first component, the incremental reliability is high. And after that, it is smaller, and it is going towards 0. So if you look at the x-axis here, number of components, you can decide where to stop. You want to stop at 2, you want to stop at 3, yeah, because this is actually translating into the cost. You add more components, you're going to add to the cost, isn't it? And then you have to maintain them, the volume will increase, the weight will increase, and so on and so forth. So this kind of analysis basically can be done, yeah, so that you can find out how many components my system will need in parallel, and that I consider to be adequate. It's again a managerial decision, right? Otherwise somebody may say, oh, why not go towards 100%, right? Why not, yeah, let it go towards 100%. What's wrong with that? Even if the number is small, so what? yeah, my reliability is going to almost close to 1, right? So it's a managerial decision, where do you want to stop? But this kind of study helps you to decide how many components in parallel you want to employ. So we can conclude, based on whatever we have discussed so far, that the addition of the first redundant component to the original system provides the largest benefit to the system. This is no surprise. That's why we call it a redundant system, right? Then the amount of improvements to system reliability reduces or diminishes as more components are added in parallel. And the x-axis relates directly to the cost. Hence, the cost-benefit analysis can be done by the managers. Now, we have talked about series, we have talked about parallel, and then we talked about series parallel. And I also showed you how many components in parallel, what is the incremental reliability. But there are some systems that are none of those. They are neither series nor parallel, nor series parallel, but they are partially redundant. Partially redundant means that there are 3 components in series and you need only 2 of them to operate. That's a partially redundant system. What is a fully redundant system? Only 1 is needed. Whether you have 2 or 3 or 4 or 5 in parallel, only 1 is needed. That's called a fully redundant system. So now I'm talking about partially redundant. 2 by 3, 2 by 4, 3 by 5, things like that. That's partially redundant. So this makes it a little bit more interesting to see how we calculate that. So use an example, always better. We have 3 components, 1, 2, and 3 in parallel, and assume that for system success, 2 out of these 3 components must be operating. So the system success is defined as 2 by 3. As long as any 2 components are up or operating, we say that the system is a success. Otherwise, it is a failure. So the states of the system, if you look at this, the states are either all the 3 components are working. That means the reliability will be R1, R2, R3, or 1 and 2 are operating but 3 is down, or 1 and 3 are operating but 2 is down, or 2 and 3 are operating and 1 is down, isn't it? You need 2 components out of the 3 to operate, any 2. So these are the various possibilities, and therefore the total system reliability will be R1, R2, R3, because all 3 are operating, plus R1, R2, component 3 is down, plus R1, R3, component 2 is down, plus R2, R3, component 1 is down. So when you add these all up, you will get the total system reliability. So in this case, now I have assumed that all these 3 components are identical, then R1, R2, R3 is all R. Therefore, Rs will become R cube plus R square Q plus R square Q plus R square Q. So 3 times R square Q. Clear? Another example. Derive the general expression for the system reliability of the following system. So this one, if nothing is stated, means it is fully redundant, right? If nothing is stated, means it's fully redundant, meaning only 1 out of these 2 is required for system success. But here it is stated it is a 2 by 3 system. So again, you need any 2 or all 3, correct, for system success. And of course, we already know that this is in series with this, is in series with this, and then all this is in parallel with 7. So you can break this up into a component called 8, you can break this up into a component called 9, and then 1, 8, and 9 can be sort of again called a component, new component 10, and 10 and 7 will give you the eventual component 11. This is just a simpler way of trying to identify the models. Yeah, if you are very, very familiar with this, you don't have to do this. You can start writing the equations and start solving. But I think it's good to understand in this way so that we know how to break down the problem into simpler problems before we arrive at the final solution. Okay. So how will we approach this? So we start from Q8 is equal to Q2, Q3. So 8, this is the component 8, parallel, fully redundant 2 and 3. Yeah. So what is the unreliability of this system, subsystem? It's Q2 times Q3. And therefore the reliability is R2 plus R3 minus R2, R3, right? I hope you still remember those equations. So this is Q8, therefore R8 is 1 minus Q8.
So R2 plus R3 minus R2, R3. Then R9, let's go back here. 9, component 9 is this one, 2 by 3 system. And there are 3 components there, 4, 5, 6. So it'll be R4, R5, R6 plus R4, R5, Q6 plus R4, R6, Q5, and so on and so forth, right? Just the way that we saw a little while ago. So that's what I have done here. R9 is given by these 4 expressions. And then finally R10. What is R10? Component 10 is a series combination of these 3. So it is R1 times R8 times R9, right? So that's what it is. R1 times R8 times R9. And then component 11. 11 is a parallel combination of 10 and 7. So it will be R10 plus R7 minus R10 times R7. So that's what it is. And then I want you to put in all the expressions and go back to the original. Yeah, go back to the original. That means I don't want 8 and 9 and 10 and 11 in the expression. I want only 1, 2, 3, 4, 5, 6, 7. So you need to simplify the expression. That's what I'm asking you to do. Okay, so you are urged to complete the exercise. How much that urging works, I do not know. Well, hopefully you will do that either in the afternoon or some other time at your leisure. One more example. I have put a lot of examples here so that it sets the tone. Consider a 3-element system, each element having a reliability of 0.9. Calculate the reliabilities of the 4 arrangements. Now I want to show you clearly which arrangement is better. Yeah, and we have to draw appropriate conclusions. So series, we all know by now series, R1 times R2 times R3, and each element is the same. So the reliability is the same at least. We don't care if the elements are not the same, but the reliabilities are the same. So 0.9 cube, right? Yeah, so that's 0.729. Now, parallel series. This configuration is called parallel series. So there are 2 parallel paths, and in each path there are components in series. So what is the reliability of this? So if you look at this 0.9 cube, 0.9 cube is the reliability of this path, correct? Yeah. And then what is the unreliability of this path? It is 1 minus 0.9 cube, correct? And this path are identical. So 1 minus 0.9 cube square is the overall unreliability of this set, correct? So what is the reliability? It is 1 minus this whole thing. I wish I could show you on the whiteboard, but as long as you can understand, it should be okay. So far okay, right? Yeah. It might get tougher as we go on. And then perhaps if there are some pens here, I can show it on the whiteboard. So this is parallel series. Now next, mixed parallel. This arrangement is called mixed parallel. So what do I have? I have 2 components in series, 2 in series, and then another series, but the 2 components are in parallel. So if we find the reliability of this, let's see, these 2 are in series. So what's the reliability? 0.9 square, right? Correct? Are you with me? I'm trying to explain here without writing on the board. These 2 are in series, so reliability is 0.9 square. What's the unreliability? 1 minus 0.9 square, correct? And then both of them are in parallel, so 1 minus of this will give you the system reliability, right? And then for this one, what is the unreliability, or rather reliability? It's 0.9, yeah, and the unreliability is 1 minus 0.9. And because both are identical, so 1 minus 0.9 square, correct? And then why do I multiply? Because this set is in series with this set. So therefore I multiply and I get a certain number, okay? Mixed parallel. Last but not least, I've got a series parallel. So this system is in series with this, is in series with this. And within a system, there are components in parallel. So this is called a series parallel configuration. So how do I calculate the numbers here? Let's go back from this. 0.9 square. 0.9 square. Yeah. What is that? 0.9 square? Parallel. And 1 minus 0.9 square is the reliability of this. Yeah. 1 minus 0.9 square, correct? Yeah. And then there are 3 systems in series. So that's where you get the cube, right? So it's exactly the same for each subset, and you get this as the reliability. So what do we conclude? We can actually put some general equations, yeah, with n parallel paths of n components. We can say that the parallel series can be written in this form as a general equation. Similarly, for series parallel, we can also write a general equation. But what we observe from the answers, series parallel is 0.97, whereas parallel series is 0.92. Can you see that? Yeah. So therefore, we show clearly that series parallel has a higher reliability compared to parallel series. Yeah. So series parallel configuration is better. If you're planning your systems, then that's one way of looking at it, how to improve the reliability when you want to connect them in series parallel or parallel series or mixed parallel and things like that. Okay?
In this scenario, we can consider like finding out the bottlenecks in the system, because the weak link, one is the system reliability. Okay, we can plan according to that, and then look into that down, then which is the weakest link,
Right.
in that, so that we can focus on that weakest link of the improving the reliability.
That's correct. Actually, in all this, I have used these numbers, right? I mean, I said to you that the reliability of the component is 0.9. How do I know that? These reliabilities or probabilities, nobody may be watching, right? These reliabilities 0.9. How do I get this number? I mean, of course, for illustration, I can use any number. But in practice, how do we get this number? This is the most important part of the problem. You don't get the right number, your analysis is all wrong. It's all haywire. So how do you collect this? This is the data collection thing that is so very critical, based on past history and also based on future predictions. You need to be able to come up with those. And many a times it's not just a single number, it's a probability distribution, which is what we'll discuss next after the tea break. Yeah, because many of the reliabilities are not distributed like with just a mean value. They have an exponential distribution or a normal distribution or Rayleigh or Weibull, gamma and things like that. Okay, so we are slowly going there. Right. So this is an exercise for you, and fortunately for you, I've given you the answer. Let's hope that sometime today or sometime later, you can see and get that same answer, okay? I calculated it last night just to be sure, and I did get that answer, so I think it's fine. Yeah, okay. So this is nice. You know how to handle this, but do you know how to handle this? Yes, anyone? We are not going to do it now, but I just want to hear your thoughts. How am I going to handle this 2 out of 4?
2 out of 4 working.
Yeah.
We can analysis 1 up, 2 up, 3 up.
Right, right. So how will you do it for this 6677?
6 is 1 unit.
So एक-एक करके कितने आएंगे मैडम? बहुत सारे आ जाएंगे, right? Is there an easier way? That's what I'm trying to ask you. There are many professors here. Professor Nangia. Permutation combination. Okay. Let me tell you the easiest way. R6 plus Q6 square. There are 2 such components. R6 plus Q6 square multiplied by R7 plus Q7 square. And you expand this. So you'll have all the terms of R6, R7. Choose the ones where at least 2 components are up and reject the other terms. That is the fastest way. Yeah. Otherwise, it will take longer. Yeah. Is it clear? Anyone who didn't follow what I said? Yeah. R6 plus Q6 square multiplied by R7 plus Q7 square, expand it and choose the terms where at least 2 components have R in the equation. There are 2 R's at least. reject the others, yeah, because that's a failure. Okay, now we move to more complex systems. Not series, not parallel, not series parallel, not parallel series, but any other type of configuration. So this is the complex system that we have chosen for now, but still not that complex. So many systems in actual practice have complex operational logic, so we need additional modeling techniques. So I'm using this example here. There are many methods to solve these complex models or complex systems, and there are at least 6 techniques that are available in the literature, and I have studied all these techniques and I have used quite a few of them in my own research, but for the purpose of this course we shall restrict ourselves to what is the most, perhaps the most powerful, and that's the cut set method. Actually the event tree method is also very good, but it keeps growing if the number of components is large. So that's why I think it's better to deal with the cut set method. Why? Because you can also program it. The cut set method is more easily programmed as opposed to the other methods. So that is the other advantage that we have. Yeah. And it is the most commonly used in engineering reliability calculations. So let's see what this method entails. First, we define a cut set. What's a cut set? It's a set of system components which, when failed, causes system failure. But we are not so interested in just a cut set. We are interested in a minimal cut set. So what is a minimal cut set? Is a set of components which, when failed, will cause failure, but if any one component has not failed, does not cause system failure. So I give you an example here. A and B, if they fail, this system will fail. This is the input, this is the output, right? So if A and B fail, everything fails. Now I ask you a question. If A, E and B fail, what happens? No, A has failed. A, E and B have failed. Input cannot go anywhere, right? That's the difference between a cut set and a minimal cut set. So if I say A, E and B is a cut set, then that's wrong, because look at the definition, which when failed causes system failure. If A and B themselves fail, then there is a failure. But if I take A, E and B, then E is not needed to fail. Yeah, it's like redundant. So therefore that is not a minimal cut set. So minimal cut set is A and B, C and D, A, E and D, and B, E and C. Yeah, you go diagonally, correct? So there are 4 minimal cut sets. There are many cut sets, I repeat, there are many cut sets. You can say A, E and B is a cut set, but it's not a minimal cut set. You need all the components in the cut set to fail, okay, for the system failure. So there are 4 minimal cut sets. I'm calling them C2, C3, C4, and these are the components of those cut sets. There are no first order cut sets. What do I mean by first order? That means any one component fails, then the system fails. That's called a first order cut set or first order system failure. Here, minimum 2 components must fail, isn't it? Either these 2 or these 2. So we have 2 second order cut sets and we have 2 third order cut sets, A, E, D and B, E, C. Yeah. So that's what we mean by no first order cut sets. So the system unreliability is obtained by the union of the 4 cut sets. This sign means union, yeah? Cut set 1, cut set 2, cut set 3, cut set 4. Now this is very complex. And imagine I have got only five components and we have to write the expression for this. I'll show you the expression for this, which is very daunting. Yeah, this is what it is. So obviously you don't want to do this. If there are 10 components, 20 components, all hell will break loose. We'll realize that our life as it is tough, and we are making it more tough by reading this thing, right? And you're going to curse me more than anything else. I wouldn't want that. So I just want to tell you essentially the process. If these are the 4 cut sets, then the elements of the cut set are in parallel. Why? Because both must fail, remember? For parallel components, both must fail, or all 3 must fail, or all 4 must fail. So the elements within a cut set must be in parallel. And through any cut set, I can get system failure. Therefore, all the cut sets are in series. Are you with me? Any cut set, as long as I have a cut set, yeah, I will have failure. So all the 4 cut sets are in series. Now, what makes it difficult here is that A is here, A is also here. C is here, C is also here. That's why when we write the equation for QS, probability of C1 union C2 union C3 union C4, we have to consider all the options. And that's why you see this unwieldy expression. Yeah. So not to worry, if for those who are really keen on mathematics, this is an excellent exercise. But if you're not, then you know I'm just going to tell you how to deal with these problems more easily. That's what engineers do. That's what we always do. We make what? Assumptions. We make approximations. So we are going to make approximation here as well. We are going to make 2 approximations. Number 1, we are going to say that the system unreliability, which is given by this expression, can be reduced to a summation of first order unreliabilities. Now, please understand the terminology. I said just now, short while ago, we don't have a first order cut set. Remember? What am I saying here? I'm saying first order unreliability. I'm not saying first order cut set. So what's a first order unreliability? Yeah. So here, C1, C2, C3, C4. This is one order only, right? Yeah. We are not going to the next higher order. So it is P probability of C1, cut set 1. Cut set 1 is A and B in parallel. So it will be QA times QB, unreliability, right? Unreliability of this QC times QD. Unreliability of this QA times QD times QE, and so on. So that's what we'll get. So this is the expression, right? And if all the components are identical, then all these Q's are the same, and therefore we can reduce it to 2Q square plus 2QQ. Yeah. So this makes the problem relatively simpler. Obviously, the end result is going to have some errors. Are we willing to accept those errors? If we are not, we must go back to the original and solve that big long equation. Engineers don't do that. We always make some assumptions. We always go for approximations. Why? Because at the end of the day, these numbers will continue to change, especially when you do long-term planning. Yeah, it's not worth looking at the details. It's better to use some approximations and then compare option 1, option 2, option 3, and so on and so forth. Okay. So that's the first way of approximating the result. The second one is neglect higher order cut sets. So we have two first order cut sets and 2 higher order cut sets. So I'm going to neglect this, I'm going to neglect this. I'm only going to consider C1 and C2. That's what I'm saying in the second approximation, neglect higher order cut sets. So I only consider C1 and C2. So QA, QB plus QC, QD. And then of course, if all of them are the same, then it becomes 2Q square. Now look at this, 2Q square plus 2QQ. And in this approximation, it's only 2Q square. But remember, if the components are highly reliable, what is the value of Q? It is 0.01, it is 0.005, things like that. So Q cube will be very, very small, isn't it? So the approximation is well worth it. But again, it depends upon how you are going to apply this, how much tolerance can you tolerate, and therefore you must use one of these 2 approximations. Okay, so the errors introduced are small, particularly if the unreliabilities are very small, meaning if the components are highly reliable. The main advantages of the cut set method, a minimal cut set method in this case, are as follows. Can be easily programmed on a digital computer, which I mentioned earlier as well. And the cut sets are directly related to the modes of system failure. And therefore, we can always do a failure modes and effects analysis. And we are able to even include the cost into the equation when we know what are the failure modes of the system. So this is a very elegant way of trying to identify the failure modes of the system. There is another exercise for you. I think there's a lot of exercises. They have a lot of work on their hands this afternoon. yeah, if they want to do it this afternoon. So nice systems here. This one is simpler. Yeah, this is the input, this is the output. This one is not as simple. Imagine doing the long way for this. I think you'll die. Yeah, simply you'll give up. So you must use approximate method, right? So what am I asking you? With approximation, find the system unreliability. Yeah, without any approximation, find the system unreliability. Yeah, that's always going to be tough. So try for the first system, but not the second system. For this one, you can do it. For this one, it'll be harder. But what are the minimal cut sets here? Let's just look at that. The minimal cut sets in this system are AB, a second order cut set, and ACD, a third order cut set. There's only two minimal cut sets. Yeah, so quite straightforward. If you use the approximate method, yeah, then it is very, very straightforward. Then for this one, how many cut sets are there? Are there any first order? No. Are there any second order? No. All are third order. So ACF, ADF, BDF, BDG, BEG, yeah, and I forgot one. ADG, yeah. ACF, ADF, ADG, BDF, BDG, and BEG, correct. So there are 6 third order cut sets, and using the approximate method is quite straightforward. Okay. Interesting questions for your doing pleasure, and I think that concludes this particular chapter. So we can take a little break if everybody is hungry. Yes, you have arranged for something, so we